Indian Standard Time, 5 minutes, grace time. Okay.
A very good evening to one and all present here. I am Suhasini B from BCA Department of Sri Ramakrishna College of Arts and Science, here to host a student-led webinar. On behalf of the CSI Region 7 chapters, I now call upon Mr. C. A. Rajashekhar, MS, Chairman CSI Coimbatore chapters, to delivering an opening remark.
Very good evening to everyone. A very good evening to all the Region 7 chapter representatives and members and my dear student members. I welcome you one and all for this nice and very informative presentation to be given by our resource person is Akash. And I hope that this meeting will really take away with give you a very good enriched knowledge and information about what is ahead of the technology here. Mr. Akash is a BCA student from Ramakrishna College, and he will be delivering the topic on flying ad-hoc networks and swarm intelligence. And on behalf of the Coimbatore chapter of CSI, as a chairman, I welcome you one and all for this very informative student meeting. And this is the second such meeting which our chapter is hosting in the Region 7 network. And I hope more to come in the years ahead. I welcome you all and all to this meeting again. Over to the MC for uh, further proceedings. Thank you.
Thank you, sir. Now I call upon Mr. R. Saravanakumar, former chairman, CSI Coimbatore chapter, to deliver a welcoming address and introduction to the guest speaker.
Thank you. So, good evening, everyone. Iniya Malai Vanakkam. On behalf of the Computer System of India Region 7, it is my privilege to welcome you all for this wonderful session. Today's session is a vital part of our monthly student-led webinar series. This particular initiative serves as a dedicated platform designed to empower our students, giving them the opportunity to transition from learners into confident presenters and subject matter experts. By providing this stage, we aim to cultivate a culture of peer-to-peer learning and professional growth, allowing students to showcase their unique research and technical insights to a broader audience. At CSI, we believe that providing these opportunities at the undergraduate level is essential for building the next generation of IT leaders. We are excited to see how today's discussion will spark new ideas and encourage more students to step forward and share their knowledge. Thank you for joining us in supporting this vibrant academic community. Now let me proceed with the speaker introduction. Akash, wait, let me continue with the speaker introduction. I completed my welcome address. Now I'm continuing with my speaker introduction. So Akash is a student currently pursuing his Bachelor of Computer Applications, BCA, at Sri Ramakrishna College of Arts and Science in Coimbatore. He has demonstrated exceptional academic initiative by publishing a research article titled A Comparative Analysis of Bio-Inspired Algorithms in Flying Ad Hoc Networks, that is FANETs, in the Journal of Contemporary Academic Research and Methodologies. His commitment to excellence was further recognized when he was named the best presenter at the second International Conference on Advances of Information Technology and Innovation in Computer Applications for Sustainable Development. He has also gained practical industry exposure through an internship program, which was focused on IoT and UI UX design using Figma. Akash possesses a strong technical foundation, including proficiency in MATLAB for simulation and research, foundational knowledge in programming languages like C, Java, and Python, ongoing learning in development operations, that is DevOps, agile methodologies, Jenkins, Docker, and cloud computing concepts. In addition to his technical and research achievements, Akash is a standout athlete. He has secured a gold medal at the state level wrestling championship and has represented the state at the national wrestling championship. Please join me in welcoming Akash to share his insights. Thank you.
Thank you, sir. Now it's time to move forward and hand over the session to Mr. S. Akash, student of BCA Department of Sri Ramakrishna College of Arts and Science.
Good evening, one and all present here. Hope my screen is visible to everyone.
Yes, it is visible, Pa.
So, good evening, one and all present here. Myself, Akash. I am a second year BCA student from Sri Ramakrishna College of Arts and Science. So, today we are going to see about flying ad-hoc networks and swarm intelligence. So, before I begin the session, I want you guys to imagine a situation where multiple drones are flying in the sky, maybe for disaster rescue, military surveillance, or delivery systems like Amazon drones. Now, imagine these drones need to communicate with each other without relying on any fixed infrastructure like towers or satellites. So the question is, how do they coordinate, communicate, and make decisions efficiently? So this is where the concept of flying ad hoc networks comes into play.
Excuse me, if possible, you can also enable your video so that audience also are able to relate whenever you talk, if possible.
So I think the connection.
Okay, fine. Go ahead.
Better.
No issues. If you have technical challenges, no issues at all. Please proceed further, Akash. Thank you.
Okay, sir. Thank you. Now, let's understand what FANET actually is. So FANET stands for Flying Ad Hoc Networks. It is a type of network where multiple UAVs communicate with each other wirelessly without relying on any fixed infrastructure. So in traditional networks, communication depends on base stations or centralized systems. So, but in FANET, there is no such infrastructure. The UAVs themselves act as nodes and form the network dynamically without any centralized powers. So now let us look at key characteristics of the FANET. First, the characteristic is it is three-dimensional space. So unlike ground-based networks where movement is limited to 2 dimensions, UAVs can move freely in all directions, including vertically, horizontally, anything. So this makes the communication more flexible, but also more complex. The second characteristic is that the FANET is highly dynamic. So UAVs are constantly moving, which means the network topology changes frequently. So because of this, the communication links between nodes can break and reconnect often. And the third characteristic is self-organization. So, or self-organizing. There is no central controller managing the network, as I said already. So each UAV independently makes decisions and cooperates with other UAVs to maintain communication. And the fourth characteristic is decentralization. Since there is no central authority, all UAVs share equal responsibility in maintaining the network. So this improves the flexibility and also the scalability, but also makes the coordination more challenging. So overall, FANET is a flexible and powerful network system, but its dynamic and decentralized nature introduces several challenges also. So now that we understand what FANET is and its key characteristics, let us move on to the main component of this network, which is UAVs. First of all, why we are using FANET? So let us look at this slide, which represents real-time surveillance and image processing. As you can see the image, this data can be used in oil pipeline monitoring, sports broadcasting, urban surveillance, etc. So this data can be in form of images or video, and it is processed in real time. So real-time surveillance means continuously monitoring an area using UAVs. So unlike traditional systems where cameras are fixed in one place, UAV can move freely and cover large areas. So this makes the surveillance more flexible and efficient. For example, in disaster situations such as floods or earthquakes, UAVs can be deployed quickly to monitor affected areas. They can capture live video and help rescue teams understand the situation better. Similarly, in security and military applications, UAVs are used for monitoring and tracking activities in real time. Now, along with the surveillance, image processing plays a very important role. The data captured by UAV is not just stored, it is analyzed instantly. So, image processing techniques are used to extract useful information from the captured images. For example, the system can detect objects, identify people, or recognize patterns in the environment. So, this helps in making quick and accurate decisions. So, now let us connect with this FANET. So in the FANET system, multiple UAVs are connected and communicate with each other. Each UAV collects data and shares it with the other UAVs in the network. This creates a collaborative system where information is distributed and processed efficiently. So since FANET does not depend on fixed infrastructure, can work even in remote or damaged areas. So this is especially useful in emergency situations where traditional communication systems are not available. Another advantage is faster response time. Since the data is processed in real time, decisions can be made immediately. So if a UAV detects a person in a disaster zone, the information can be instantly shared with rescue teams. Similarly, in traffic monitoring, UAV can detect congestion and help in managing traffic flow. Now, let us consider how multiple UAVs improve the system. If only one UAV is used, the coverage area is limited. But in a FANET, multiple UAV can work together and cover a much larger area. They can also share information with each other, which improves accuracy and reliability. And UAV may detect an object, and another UAV can confirm it from any angle. This improves the overall quality of surveillance. However, there are also challenges. Since UAVs are constantly moving and maintaining communication between them can be difficult. Also, processing large amount of data in real time requires efficient algorithms. So this is where the intelligent techniques such as swarm intelligence and swarm intelligence become important. They help in managing communication and decision making in such dynamic environments. So overall, this slide shows how UAVs combined with FANET enable real-time surveillance and image processing. So this makes the system more efficient, flexible, and suitable for real-world applications. Now let us move on to the next slide and understand UAVs in detail. So in this slide, in real-world scenarios, disasters such as earthquakes, floods, and cyclones or wildfires can severely damage communication infrastructure. In such situations, traditional communication systems like cellular towers or wired networks may fail completely. So this creates a major problem because rescue teams cannot coordinate effectively and efficiently, and it becomes difficult to assess the situation on the ground. This is where UAV and FANET plays a crucial role. So UAV can be deployed quickly into the affected areas without requiring any existing infrastructure. And since they are aerial vehicles, they can easily access regions that may be difficult or dangerous for humans to reach also. So in this case, a flood, in case of a flood, many areas may be submerged. So making it impossible for rescue teams to enter immediately. Where UAV can fly over these areas and capture real-time images and videos. When multiple UAVs are deployed, they form a flying ad-hoc network. So in this network, each UAV acts as a node and communicates with other UAVs. So this allows the systems to function even without any central infrastructure, as I said already. The UAV can share information with each other and relay it back to rescue teams or control centers. So this creates a temporary communication network that is highly useful in emergency situations. One of the major advantages of using FANET in disaster management is real-time monitoring. The data collected by UAV is transmitted instantly, which helps authorities understand the situation as it evolves. So They can identify areas with maximum damage or locate people who are trapped and need immediate assistance. Another important application is search and rescue operations. So UAVs equipped with cameras and sensors can scan large areas quickly and efficiently. Using image processing techniques, the system can detect human presence, identify movement, and or recognize patterns that indicate survivors. This significantly improves the speed and accuracy of rescue operations. In addition to this, UAV can also be used for delivering emergency supplies also. So in disaster affected areas where roads are blocked or inaccessible, UAVs can carry essential items such as food, medicine, or communication devices for the affected people also. This ensures that help reaches people even in the most difficult conditions. So another advantage is coverage. A single UAV has limited range, but in a FANET system, multiple UAVs can work together and cover a much larger area. They can coordinate with each other and avoid redundancy, ensuring efficient use of resources. And since the UAVs are constantly moving, maintaining stable communication between them can be difficult. Also, energy consumption is a major concern because UAVs operate on limited battery power. Therefore, efficient algorithms are required to manage communication and optimize performance. So overall, FANET provides a powerful solution for disaster management by enabling fast deployment, real-time monitoring, and efficient communication. Now that we understand how FANET is used in disaster management, let us move on to the next concept. So this is about smart agriculture, which is precision farming. Agriculture is a very important sector, and improving efficiency in farming can have a significant impact on food production and resource management. So traditional farming methods often rely on manual observation, which can be time consuming and less accurate. So this is where the UAVs and FANET comes into play, which gives the major improvements to the agricultural sectors. So they can capture high resolution images and videos of crops over large areas time to time. This helps farmers understand the condition of their crops more effectively. UAVs can detect areas where crops are not growing properly or where there may be issues such as pests or diseases. So using image processing techniques, these problems can be identified at an earlier stage, which can improve the quality of the products. So the farmers take timely action and prevent further damage. Another important use is soil and irrigation monitoring. UAV can analyze soil conditions and identify areas that require more water or nutrients. So in that case, this helps in optimizing irrigation and reduce water wastage. Now, when multiple UAVs are used in large agricultural fields, they form a FANET, which is flying ad-hoc network, obviously. In this network, UAVs communicate with each other and share data. So this allows them to coordinate their movements and cover large areas efficiently. For example, one UAV can scan one part of the field while another UAV scans a different area. This results in reducing time and the time required for monitoring and increases efficiently. Another advantage is real-time data analysis. The data collected by UAVs can be processed instantly, which allows farmers to make quick decisions. For example, if a certain area is identified as unhealthy, fertilizers or pesticides can be applied only in that specific region. So this is known as precision farming, where resources are used efficiently and only where needed. This not only improves crop yield, but also reduces cost and environment impact. FANET also enables better coordination between UAVs. Since the network is decentralized, UAV can continue to operate even if one node fails. This ensures reliability and continuous monitoring over the farm overall. However, there are also challenges in agricultural environments. Large fields may have connectivity issues, and UAVs must maintain communication over long distances. Also, energy consumption is an important factor since UAV need to operate for extended periods. Therefore, efficient algorithms are required to optimize communication and movement. And This is where the swarm intelligence becomes useful, as it helps UAVs coordinate efficiently and adapt to changing conditions. So overall, FANET plays a crucial role in smart agriculture by enabling real-time monitoring, efficient resource usage, and improved crop management as well. It helps farmers make better decisions and increases productivity. So now let us move on to the next application, that is smart cities and infrastructure monitoring. A smart city uses advanced technologies to improve the quality of life for people by making urban services more efficient and intelligent. These services include traffic management, surveillance, environment monitoring, and infrastructure maintenance. In such environments, continuous monitoring and communication are very, very important. This is where UAVs and FANET plays a significant role. UAV can be used to monitor different parts of a city in real time. Unlike fixed cameras, UAV can move freely and provide dynamic coverage also. This allows authorities to monitor areas that may not be covered by traditional surveillance systems. So, for example, in traffic management, UAVs can be deployed to monitor road conditions. They can detect traffic congestion and accidents or unusual situations. And this information can be shared instantly with traffic control systems, allowing authorities to take quick actions upon the complaints. This helps in reducing congestion and improves traffic flow. Another important application is urban surveillance. UAVs can be used to monitor public spaces for safety and security. They can capture real-time video and help in identifying suspicious activities. This enhances public safety and supports law enforcement agencies. Now, when multiple UAVs are used in smart city, they form a FANET. In this network, UAVs communicate with each other without relying on fixed infrastructure. This point will be repeating in all the sections. So the decentralized nature of a FANET ensures that the system remains functional even if some nodes fail. Another important application is infrastructure monitoring. UAVs can inspect buildings, bridges, and other structures. They can detect damage, cracks, or any maintenance issues as well. This helps in preventing accidents and ensuring safety. So environmental monitoring is also a key application. UAV can measure air quality, monitor pollution levels, and observe environmental changes. So this can be used to improve urban planning and environmental protection. One of the major advantages of using FANET in smart cities is real-time data sharing. Since UAVs are communicating with each other, information can be distributed quickly across the network. This allows faster decision making and better coordination. Another advantage is flexibility, where UAVs can be deployed as needed and can adapt to different situations. For example, during large public events, additional UAVs can be deployed for monitoring and security. However, there are also challenges. Managing a large number of UAV in a city environment can be complex. There may be obstacles such as buildings and communication can be affected by interferences as well. Also, ensuring privacy and security is an important concern in urban areas. Therefore, efficient algorithms and proper regulations are required. This is where swarm intelligence helps in coordinating UAV movements and communication efficiently. So overall, FANET plays a key role in enabling smart city applications while providing real-time monitoring, efficient communication, and flexible deployments. So it can improve urban services, enhancing the quality of service. Now let us move on to the next application, that is military and defense surveillance. In military operations, communication and coordinations are extremely important. However, these operations often take place in remote or hostile environments where communication infrastructure may not be available or may be intentionally disrupted. So this creates a major challenge for effective coordination and decision making, where UAV and FANET provide a powerful solution. UAVs can be deployed for surveillance and reconnaissance missions. They can fly over large areas and capture real-time data, including images and videos. This helps in monitoring enemy movements and understanding the battlefield situations. So when multiple UAVs are deployed, they form a flying ad hoc network. In this network, UAVs communicate with each other directly without relying on fixed infrastructure. This makes the system highly flexible and suitable for dynamic environments. So, UAVs can continuously monitor an area and provide instant updates. This helps commanders make quick and informed decisions. For example, if an enemy is detected, the information can be immediately shared across the network. Another important application is target tracking. UAVs can track moving targets and share this information with other UAVs or ground units as well. This improves accuracy and coordination during operations. In general, FANET also enables coordinated missions. Multiple UAVs can work together to perform tasks such as area surveillance or search operations, strategic monitoring, etc. They can divide the area among themselves and ensure complete coverage. And this increases efficiency and reduces the chances of missing important information. Another advantage is robustness. Since FANET is decentralized, there is no single point of failure. Even if one UAV is destroyed or loses connection, the network can continue to function using other UAVs. This is very important in military scenarios where reliability is critical. In addition to surveillance, UAVs can also be used for communication relay. They can act as intermediate nodes to transmit information between ground forces and the UAVs. So this is useful in situation where direct communication is possible, not possible, or impossible. However, there are also challenges in military applications. Security is a major concern. The communication between UAVs must be secure to prevent interception or hacking. Also, the environment may include obstacles, interference, or hostile conditions that affect communication. Another challenge is energy management. As UAV need to operate for longer durations, to address these challenges, intelligent algorithms such as swarm intelligence are used. These algorithms help in optimizing communication, improving coordination, and adapting to changing conditions. So overall, FANET plays a vital role in military and defense applications by providing real-time surveillance and security communication and efficient coordinations. So it enhances situational awareness and supports strategic decision making in critical operations. Now let us move on to the next application, which is media broadcasting and event coverages. In today's world, live broadcasting has become very important, especially for events such as sports matches or concerts or public gatherings and news reportings or any events also. Nowadays, UAVs are also used for photography as well. So these systems have limitations in terms of coverage, flexibility, and mobility. This is where UAVs provide a significant advantage. UAVs can capture aerial views and dynamic angles that are not possible with fixed cameras or human-based cameras, which is controlled by humans in basic. So this is where FANET plays an important role. In a FANET system, UAVs communicate with each other and share data in real time. This allows multiple drones to work together and cover different angles of the same event. For example, in a sports event, one UAV can focus on the players, another can capture a wide-angle view of the stadium, and another can follow specific actions. All this data can be combined to create a complete and immersive viewing experience. Another important advantage is real-time data transmission. The video captured by UAVs can be transmitted instantly to broadcasting centers. This enables live streaming of events without delay. FANET ensures that this communication is continuous and reliable, even if some UAVs move out of direct range. Another application is news reporting. UAVs can be used to cover events such as protests or accidents or any natural calamities. They can quickly reach the location and provide live updates. This improves the speed and quality of news reporting, and FANET also helps in coordination between multiple UAVs. And UAVs can share the information about their position and movement, which helps in avoiding collisions and ensuring smooth operation. This is very important in crowded environments such as stadiums or public events and public gatherings. Another advantage is flexibility. UAV can deployed quickly and can adapt to different types of events. So, and it can also high quality videos requires large amount of data to be transmitted in real time. This is the one major challenge is bandwidth and data transmission. Another challenge is safety and regulations, especially when UAVs are used in crowded areas. Proper control and coordination are required to avoid accidents. Energy consumption is also a concern as UAVs need to operate continuously during the entire events. So to address these challenges, efficient communication and coordination techniques are required. This is where swarm intelligence helps in managing UAV behavior and swarm optimizing performance. So overall, FANET enhances media broadcasting and event coverage by communication, providing dynamic views, real-time communication, and efficient coordination between UAVs. Just a minute. Okay, now let's move on to the next one, that is delivery and logistics. So in recent years, there has been a significant increase in the use of UAVs for delivery services. It's obviously an emerging technology where companies are exploring drone-based delivery for transporting packages such as food, medicine, or essential goods. The main goal is to make delivery faster, more efficient, and less dependent on ground transportation. So traditional delivery systems rely on vehicles that travel on roads. This can lead to delays due to traffic congestion or road conditions or distance. In contrast, UAVs can fly directly from the source to the destination, reducing delivery time significantly. Now, when multiple UAVs are used for delivery, coordination becomes very important. This is where the FANET plays a key role. In a FANET system, multiple UAVs communicate with each other and coordinate their movements without relying on fixed infrastructure. So this allows the system to manage multiple deliveries efficiently. For example, UAVs can share information about their routes, positions, and delivery status. And this helps in avoiding collisions and optimizing delivery paths. Since UAVs are connected through FANET, their location and status can be monitored continuously. And this improves transparency and allows better management of delivery operations. One important application is medical delivery. UAV can be used to deliver medicines, vaccines, or blood samples to remote or hard to reach areas. This is especially used in emergency situations where time is critical. Another advantage is scalability. As the number of UAVs increases, FANET can handle communication and coordination efficiently. The decentralized nature of network ensures that the system remains functional even if some UAVs fail. However, there are also challenges in UAV-based delivery system. One challenge is navigation and obstacle avoidance. UAVs must be able to detect and avoid buildings, trees, or any other obstacles. So, another challenge is energy consumption. As UAVs have limited battery life, efficient route planning is required to minimize energy usage. There are also regulatory and safety concerns, especially in urban environments. Ensuring safety operations and compliance with regulations is very important. This is where intelligent algorithms such as swarm intelligence help in managing coordination and optimizing performance. Now, let us move on to the next concept, that is UAV, unmanned aerial vehicles. So, UAV stands for unmanned aerial vehicles. It is an aircraft that operates without a human pilot on board. UAV can be controlled remotely by a human operator, or they can operate autonomously using pre-programmed instructions and onboard systems. In the FANET, these UAVs act as a node that communicate with each other and form the network. Now let us look at the classifications of UAVs. The first classification is based on structure. UAVs can be fixed wing, rotary wing, or hybrid. Fixed wing UAVs are similar to aeroplanes. They are efficient for long distance travel and can cover larger areas, but they require a runway or launching mechanism. Whereas rotary wing UAVs such as quadcopters can take off and land vertically. They are more suitable for hovering and precise movements, but they consume more energy compared to fixed beam UAVs. Hybrid UAV
இதோட கண்ணிக்கே நான் சொல்லியிருக்கேன்
Abhinay, can you please mute? So, hybrid UAVs combine features of both fixed wing and rotary wing systems. They provide both long capability and vertical takeoffs, making them versatile. The next classification is based on size. UAVs can be categorized as nano, mini, or large. Nano UAVs are very small and lightweight, often used for indoor or short-range applications, while mini UAVs are slightly larger and are commonly used for surveillance and monitoring. Large UAVs are used for long-range missions and can carry heavier payloads. The third classification is based on control. UAV can be remotely controlled or autonomously, or also semi-autonomously. So remote control UAVs are operated by humans in real time. Autonomous UAVs operate independently using algorithms and sensors, whereas semi-autonomous UAVs combine both approaches, where some tasks are automated while others are controlled manually. So these classifications help us understand the capabilities and limitations of different UAVs in a FANET. Depending on the application, different types of UAVs can be used. Now that we understand UAVs, let us move on to the next component, which is UGVs. So UGV stands for Unmanned Ground Vehicles. As the name says, UGVs are unmanned vehicles that operate on the ground. These vehicles are used for navigation and as well for performing tasks without human interventions. Unlike UAVs that operate in the air, UGVs move on terrain such as roads, rough surfaces, or uneven environments. UGVs are widely used in applications like military operations, surveillance, and also search rescues. Now let us look at the classifications of UGVs. The first type is wheeled UGVs. These vehicles use wheels for movement and are best suited for structured environments like roads or flat surfaces. They are fast, efficient, and consume less energy compared to other types. However, they are not suitable for rough or highly uneven terrains. And the second type is tracked UGVs. So these vehicles use tracks instead of wheels, similar to tanks, as you can see in the image. They provide better stability and can operate efficiently on rough or off-road terrains. And tracked UGVs are commonly used in military and rescue operations where terrain conditions are challenging. However, they are slower and consume more energy compared to wheel vehicles. And the third type is legged UGVs. These vehicles use legs for movement. It is similar to animals or robots like humanoid robots. They are capable of navigating very complex environments such as climbing stairs or moving over obstacles. However, they are more complex to design and control. So each type of UGV has its own advantages and limitations depending on the terrain and applications. And UGVs operate and satellite signals are unavailable, such as tunnels or dense urban areas. In such cases, alternative navigation methods and cooperative communication like FANET becomes essentials. Now next comes AUV, that is autonomous underwater vehicle. An AUV is an underwater robot that operates without direct human intervention. These vehicles are designed to work in marine environments such as oceans, seas, and lakes. Unlike UAVs and UGVs, AUVs operate underwater, where communication and navigation are more challenging due to limited signal propagation. AUVs mainly used for applications like ocean exploration, environmental monitoring, underwater mapping, and military surveillance, etc. So classifying this, These can be classified into 3 types. The first type is torpedo-shaped AUVs. These are streamlined vehicles designed for designed for long-range missions. Their shape produces water resistance, allowing them to travel efficiently over long distances. And the second type is open frame AUVs. So these have a more flexible structure and are used for tasks that require interaction with the environment, such as inspection or manipulation. They are often used in industrial applications like pipeline inspection or underwater construction. And the third type is glider AUVs. These are designed for energy efficient operation. They use continuous propulsion. They move by changing buoyancy, allowing them to glide through water. This makes them suitable for long duration missions where energy conservation is important. Each type of AUV is designed for specific tasks depending on the mission requirement. While UAV operate in air and UGV operate on land, AUVs extend unmanned systems into underwater environments. So this shows how unmanned systems can operate across different domains. Now, let's move on to the next topic, which is the most important topic, why we are using swarm intelligence. So basically, a collective behavior of simple agents working together without central control. So this concept is inspired by natural systems such as ants, bees, and birds. Even though each individual agent follows simple rules together, they are able to solve complex problems efficiently. Now let us relate this to FANET. As we discussed earlier, FANET is a highly dynamic network. UAVs move rapidly, communication links break frequently, and the network topology keeps changing. In such environment, centralized routing or control is not practical, because if we rely on the central system, it may fail or become inefficient due to constant changes. So this is where the swarm intelligence becomes useful. And the key feature is decentralized control. There is no central authority controlling the systems. All agents operate independently and coordinate with each other. And the second feature is energy efficiency. Swarm-based approaches help in finding optimal paths and reducing unnecessary communication, which saves the energy. And this is where this is very important in FANET, because UAVs have limited battery power. The third feature is self-organizing. The system can organize itself automatically without external control. This is useful in dynamic environments where manual control is not possible. And the fourth and the final feature is adaptability. Swarm intelligence allows the system to adapt to changes in the environment. For example, if a communication link breaks, the system can break. The system can break and the communication cannot last longer. So this is very important in swarm intelligence. And the next up, so in simulation part, we are using MATLAB instead of NS3. Why? Because in real world scenarios, implementing FANET requires physical testbed environments. This means we need actual UAVs, communication systems, and controlled environments to test the network. However, such testbed environments are not easily available. They require expensive hardware, proper infrastructure, and controlled conditions. Because of this, the accessibility becomes a major limitation. Not every researcher or student has access to such facilities. So this is why we rely on simulation tools. Now coming to MATLAB, provides a flexible and easy to use environment for simulation. So the main advantage is it is easy to implement algorithms and strong visualization and fast deployments and beginner friendly. I am also a beginner as well. So compared to NS3, MATLAB is much more easier, and in the development basis, MATLAB is much easier, and it also provides higher visualization compared to NS3. On the other hand, NS3 is a complex setup which focuses on network protocols, and it provides much lesser visualization techniques, and it is very hard for beginners. So we can see the table, meta heuristic algorithms. Among these, I have selected the swarm-based algorithms. I am using the first three: particle swarm optimization, artificial bee colonies, and ant colony optimization, as these are the most basic and foundational algorithms in swarm-based algorithms. And next up, we'll dive deep into in these algorithms. So these three algorithms are part of swarm intelligence and are inspired by natural systems. Each of these algorithms have unique characteristics that make them suitable for solving complex optimization problems. In a finite environment, we need efficient routing, adaptability, and fast decision making. Traditional routing methods are not effective because the network is highly dynamic. So we use swarm intelligence algorithms to handle these challenges. Now let us look at the ant colony optimization first. So it is a pheromone-based path selection. While, for example, in real life, ants find the shortest path between their nest and food source by using pheromone trails. So pheromone is a chemical which is secreted by ants, which will be followed by the other ants as well. So this makes ACO very effective for routing problems where we need to find optimal paths between nodes. The ACO algorithm follows the exact form like an ant. And the next is particle swarm optimization, or PSO. PSO is inspired by movement of birds in a flock. Each particle adjusts its position based on its own experience and the experience of the group. So this allows the PSO to converge quickly towards the optimal solution. So PSO is useful when we need fast convergence and quick decision making. And the third and the last algorithm is artificial bee colony, or ABC. ABC is inspired by the foraging behavior of bees. Bees explore and exploit food sources efficiently. This allows ABC to balance exploration of new solutions and exploitation of known good solution. So basically, for instance, if there is 50 UAVs, 25 will go for exploration and other 25 will go for exploitation. So this makes it suitable for dynamic environments like FANET. So each of these algorithms has its own strengths. By comparing these three algorithms, we can analyze which one performs better under different conditions. So ACO is inspired by behavior of ants and searching for food, as I already said. In nature, ants move randomly in search of food, and while moving, they leave a chemical substance called pheromone on the ground. When other ants detect this pheromone, they are more likely to follow that path. Over time, shorter paths accumulate more pheromone because ants travel them more frequently. As a result, the colony gradually converges to the shortest path between the nest and the food source. This natural behavior is used as the basis for the ACO algorithm. In our case, UAVs behave like ants, and the goal is to find the best communication path between the nodes. And the basic steps are: first, it will initialize the pheromone and calculates the probability of which time it will go to the goal, or how much energy it consumes, like that, and selects the path, which one is optimal path for reaching the goal more efficiently with lower time and maintaining higher energy efficiency. And update pheromone, which is the they also update the pheromone trails, which is more likely to be used, and repeat the processes. Next up is PSO. So as I already said, it is inspired by a behavior of birds flying in a flock or fish swimming in a school. In nature, when birds search for food, they do not move randomly. So each bird adjusts its movement based on its own experience and also based on the movement of nearby birds. So this collective behavior helps the group quickly find the best location, and this idea is applied in PSO. So in this algorithm, each solution is represented as a particle. These particles move through the search space to find the optimal solution. Now let us go to steps of PSO. First, it will initialize the position of every UAVs. It will update the position where it's starting and update the velocity. So each particle updates its velocity based on two important factors. The first factor is its personal best position, which is the best solution it has found so far. And the second factor is the global best position, which is the best solution found by any particle in the group. By combining these two factors, the particle decides how to move and how efficiently it can go through the goal. And the last one is update best values. So if the new position is better than the previous best, the particle updates its personal best. Similarly, if any particle finds a better solution, the global best is also updated. So these steps are repeated until the algorithm converges to an optimal solution. In the context of FANET, PSO helps in quickly finding optimal or near optimal solution for routing and positioning. Since it converges faster compared to some other algorithms, it is useful in a situation where quick decision making is required. However, it may sometimes get stuck in local optima, which is a limitation. So let us see what is ABC. So ABC is inspired by foraging behavior of honeybees. In nature, bees search for food sources and share information with other bees in the colony. Some bees explore new areas while others focus on known good food sources. This balance between exploration and exploitation helps the colony find the best food sources efficiently. This idea is applied in the ABC algorithm as well. So the first step is calculating fitness. Each solution is evaluated based on how good it is. This is known as the fitness value. So better solutions have higher fitness values. And the second step is assigning probability. Based on the fitness values, probabilities are assigned to different solutions, and solutions with higher fitness have higher chance of being selected. And the third step is exploration and exploitation. In this step, the algorithm decides whether to explore new solutions or exploit existing good solution. Exploration helps in discovering new possibilities, while exploitation focuses on improving known solutions as well. And the final step is updating position. Based on the exploration and exploitation process, new solutions are generated and updated. These steps are repeated until the algorithm finds an optimal or near optimal solution. In the context of FANET, ABC is adapting to dynamic changes in the network. Since it balances exploration and exploitation, it can handle changing conditions effectively. So next, we'll go into the simulation settings which I have used. So basically, I have these are the parameters define how our FANET system is modeled in the simulation. The first parameter is the number of UAVs, which is 20. So this means that 20 UAVs are used to form the network. Each UAV acts as a node and communicate with each other UAVs. The number of UAV affects the network density and connectivity. If the number is too low, the network may become disconnected. If it is too high, it may increase complexity and communication overhead. And the next parameter is area size, which is 240 by 240. This represents the spatial region in which the UAVs operate. A larger area means UAVs are more spread out, which can reduce connectivity. A smaller area increases the chance of communication, but may lead to congestion as well. The next parameter is maximum height, which is 70. So this defines the vertical limit of UAV movement. Since FANET operates in three-dimensional space, height plays an important role in communication and coverage. The next parameter is number of iterations, which is 400. This represents how long the simulation runs. Each iteration corresponds to a time step where UAV positions and network conditions are updated. A higher number of iterations allow us to observe long-term behavior and performance. The next parameter is communication range, which is 60. So this defines the maximum distance within which two UAVs can communicate. If two UAVs are within this range, a communication link can be established. If they move outside this range, the link is broken. This parameter directly affects connectivity and network stability as well. So finally, we can consider different terrain types, which include mountain, urban, desert, and ocean. Each terrain introduces different conditions that affect UAV movement and communication. For example, urban environments may have obstacles while mountainous terrains introduce elevation changes. By testing different terrains, we can evaluate how the algorithms perform under different real-world conditions. So overall, the simulation setting helps us create a realistic environment to analyze FANET performance. So now let us understand the simulation setup. Let us move on to the performance metrics used to evaluate the system. So I have used 6 performance metrics. They allow us, performance metrics are important because they help us to measure how well the network is functioning. They allow us to compare different algorithms and understand their efficiency under different conditions. The first metric is energy consumption. Energy consumption represents the amount of power used by the UAVs during communication and movement. And the network lifetime indicates how long the network remains active before nodes start failing due to energy depletion or disconnections. And the PDR stands for packet delivery ratio, which measures the ratio of successfully delivered packets to the total number of transmitted packets. A higher PDR means better communication and reliability. And the fourth metric is packet loss ratio, which is PLR. So PLR represents the ratio of packets that are lost during transmission. It is a vice versa of PDR. A lower PLR indicates better network performance. And the fifth metric is route stability. Route stability refers to how stable the communication paths are between UAVs. In a highly dynamic network like FANET, maintaining stable route is fewer links, failures, and better communication continuity. And the final metric is delay. Delay represents time taken for data to travel from the source to the destination. So lower delay is important for real-time applications such as surveillance and emergency response. So overall, these metrics help us to evaluate the performance of different algorithms in terms of efficiency, reliability, and stability. Now, that we understand how performance is measured, let us move on to the algorithms. Let us dive deep into the simulation. Just a minute, I will share my screen. So it is visible, right? As you can see, this is the program which I have used. So as I said, I have used ant colony optimization and artificial bee colony and particle swarm optimization. So basically, we can enter choices between 1, 2, 3 and select terrains by inputting the number like 1, 2, 3, 4, 5 or anything. So the global parameters are presented here. Now, let me just simulate this program. Once the program is run, it asks for choices. So it's a ant colony optimization, which is 1. And the terrain, we can select ocean, for instance, which is 4. Keep enter. And we can see the simulation. Yeah. So the black color lines are the FANET communication between the UAVs, and the green color cylindrical object.
Actually, the simulation screen is not visible, so better you share the entire screen. Then only it will be visible.
Okay, sir. So this is the simulation setup. So the black colored lines are the FANET communication between the UAVs. As you can see, only 2 UAVs doesn't have FANET communication. as it is very long to very distant to other UAVs, so it cannot communicate with each other. And the green cylindrical part is where the UAVs should reach, and basically it is the goal where they should reach. Now let's see other terrains as well. I will run the program again. So let's take ABC for this time, which is 2, and mountain region, which is 1. As you can see, in this case, drones moved much faster than the previous algorithm, because ABC is much faster compared to the previous algorithm. So even before they will have FANET communication, but as it is a faster process, we cannot see the FANET communication, and it has already reached the goal also. So likewise, we can simulate the program, and we can also compare these values as well. So I can show that also. So if I run this program, the Excel, the data will be shared in an Excel file, which will be automatically stored in my system, and it also generates images of bar diagrams for comparing these algorithms. So before that, see, in this location, the image and the Excel will appear once the program is run. So let us see how it works. See, Excel file is generated successfully. So now let's go and see. We can see the Excel file, which has the data which gained from running the data. So this is the data generated, and the images are generating as well. It will generate 6 images, and it will be stored automatically in the same location. So yeah, all the images are generated. So we can see for mountain ACO, energy consumption is 19.90, and the data varies for all the algorithms as well, depending on the terrains and the all other terrains and algorithms. We can see the data which is generated while running the program. We can also see the best algorithm in all other terrains. So in the mountain terrain, ACO is more suitable compared to other ones. So in the urban area, PSO is the best algorithm, and the desert is also PSO is more efficient, and and in ocean, ACO is better. So this is evaluated based on the bar diagram images which are recently generated. As you can see the images. So in delay comparison, you can see the legend here. Blue one shows the ACO, orange one shows the ABC, and PSO shows the yellow one. So in our case, delay should be lesser to highlight its efficiency. So here ACO is more delayed due to delayed communication. And in energy consumption comparison, PSO is higher. So PSO consumes more energy. And in network lifetime comparison, all the terrains and all the algorithms have same amount of time, network lifetime. And packet delivery ratio comparison, there are minute changes which we can see in all the terrains. And packet loss ratio is also the same. Only minute changes are there. And in route stability comparison, in every algorithms, route comparison is stable. So all the values are same. as we already saw the delay one. Okay. Let me just conclude this session. Just a minute. Yeah. Next. So we'll see the future scope of FANET with swarm intelligence. So looking at the future scope of FANET, swarm intelligence, the focus is mainly on making the system more intelligent, autonomous, and scalable. At present, routing and coordination are handled using algorithms like ACO, PSO, and ABC, which are effective, but still follow predefined rules. Wait a minute. But still follow predefined rules. In the future, we can integrate machine learning and deep learning techniques so that the network can learn from its environment and adapt in real time. This means UAVs will not just follow programmed behavior, but they will be able to make smarter decisions based on network conditions such as mobility, link failures, and congestion. This will significantly improve reliability and efficiency. Another important direction is the integration of advanced communication technologies like 6G. FANET applications such as surveillance, disaster response, and real-time monitoring require very low latency and high data rates. With 6G, we can achieve faster communication and more stable connectivity between UAVs. This will allow large-scale drone swarms to operate together efficiently, which is essential for applications like smart cities, military operations, and wide area environmental monitoring, which you have seen earlier. At the same time, there is a strong push towards fully autonomous swarm coordination. Currently, some level of human intervention is still required, but in the future, UAV swarms will be able to operate independently with decentralized control. Using advanced swarm intelligence techniques, these UAVs can coordinate among themselves, divide tasks intelligently, and adapt to dynamic environments without relying on a central controller. This makes the system more robust and suitable for unpredictable scenarios. Another key area is the use of edge computing in FANET. Instead of sending all data to central system for processing, UAVs will be capable of processing data locally. This reduces communication delay and enables faster decision making, which is especially important in time-critical situations like disaster management or military missions. It also reduces network load and improves overall efficiency. Energy optimization is also a major focus for future research. Since UAVs are battery powered, energy constraints directly affect network lifetime. So the future system will include energy-aware routing techniques that optimize power usage. Additionally, advancements such as solar-powered UAVs and improved battery technologies will help extend operational time and make FANETs more sustainable. Finally, one of the most promising directions is multi-domain integration. Instead of operating only in the air, future systems will involve coordination between UAVs, UGVs, and AVs all together. This means communication and collaboration across air, land, and underwater environments, such as integration will enable more comprehensive solution for complex applications like research and rescue, environmental monitoring, and defense operations as well. Overall, the future of FANET lies in combining intelligence, advanced communication, and cross-domain collaboration to build highly adaptive and efficient network systems. So, let me conclude my presentation. In this work, we studied flying ad hoc networks, which enable communication without relying on any fixed infrastructure. This makes FANET very useful in real-world scenarios like disaster management, military operation, and remote area communication. However, FANET is highly dynamic because UAVs are constantly moving and network topology changes frequently. This creates challenges such as unstable communication, frequent link failures, and increased delay. To address these challenges, we used swarm intelligence techniques. Swarm intelligence, where each node makes decisions based on local information while still contributing to the overall network performance. We implemented 3 swarm intelligence algorithms: ant colony optimization, particle swarm optimization, and artificial bee colony. Each of these algorithms has its own strengths. ACO is effective in finding reliable routing paths by using pheromone-based path selection. PSO provides fast convergence, which helps in quick decision making. And ABC offers a balance between exploration and exploitation, making it suitable for dynamic environments. We implemented these algorithms in MATLAB and evaluated their performance using different metrics such as energy consumption, packet delivery ratio, and route stability. So the results show that swarm intelligence improves overall network performance in FANET. It helps in reducing energy consumption, improving packet delivery, and maintaining stable communication. So overall, swarm intelligence transforms FANET into a more adaptive, efficient, and reliable communication system. This allows the importance of using intelligence algorithms in dynamic network environments as well. So I record my sincere gratitude to CSI for giving me this opportunity. And now I'm open for questions.
So Akash, really a good presentation. Thank you for
Thank you, sir.
this presentation. Really well done. I posted a couple of questions. Maybe you can take a look at it in chat and see if you have some answers. So one of the thing is you talk about swarm
Yes, sir.
communication using FANET, right? Have
Yes, sir.
you also looked up any inter-swarm communication? Does FANET support inter-swarm communications? Because that could mean, who's the leader of the swarm and then, connecting with another swarm and communicating. Is there any such architecture that's available? Or have you gone through any such, have you come across any such architecture?
Sir, as if I am a beginner also, I'm concentrating more on this FANET communication only. So I haven't
Sure.
started working on inter-FANET communication, sir.
Sure. Okay. No, maybe, in future when you go in depth, this might come up, for your research areas. The other thing was, regarding the simulation itself. Have you considered adding weather parameters? It could be humidity, cloud cover, temperature. All these factors will impact the communication efficiency and the performance in terms of speed and of the swarm itself. So, do you have a thought about how you can introduce those parameters in your simulation itself?
So thanks for your good dimension, sir. We can work on it as well. I'll look into working on it sooner. I think it can be implemented in this program as well. So I'll definitely look into integrating it, sir.
Wonderful. Because I think I would urge you to look into it if you have the time and the guidance for it. The reason I say that is because you might actually find a different architecture, a different algorithm may be best suited when you start introducing the atmospheric and weather parameters into your simulation. It may not be the ABC or the PCO algorithm, but it could be something that you have not so far considered. Okay, so I would urge you to look at those parameters, atmospheric parameters, to be brought into the simulation as well. Okay. Well done.
Definitely.
Well done.
Definitely, sir.
Good work.
Thank you, sir. Thank you so much, sir.
Thanks for educating us on all these aspects.
It's my
Something
pleasure,
that we have not
Thank
seen in normal day discussions or projects. But yeah, this is really interesting. Thank you. Thank you for entertaining us.
Thank you, sir. It's my pleasure.
Akash,
Any other questions?
I just have one question.
Yes, sir.
I mean, when we scale up from a few drones to a large swarm, the communication overhead can become sort of massive, right? You
Yes,
also
sir.
done some research on bio-inspired algorithm. So how
Yes,
does
sir.
it help you in managing this particular complexity?
So when we are using in a larger terrains, the communication may easily damaged, or it is not easy to communicate between the UAVs. Sir, can you just repeat the question once more?
See, when we scale up, when we increase from few drones to a large swarm, large number
Yes,
of
sir.
drones, the communication overhead, that is the additional load, can become too much, right? Massive, right?
Yes, sir.
So I just want to know, how does your research on bio-inspired algorithms help in managing this particular challenge or complexity?
So that performance metrics taken into account, which is overhead. So it is not taken into account for this work. It is focused only on packet drop and delivery, sir.
Okay, thank you. Maybe each drone might need to communicate with its immediate neighbor alone, not with all the drones, right? It's like a flock of birds, if I'm not wrong, right? Correct me if
Yes,
I'm
sir.
wrong. Okay, thank you.
Yes,
Thank
sir,
you.
right.
Well done.
So
Great
I'd just like
presentation.
to add
Thank
on
you, sir.
that,
Yeah.
Saranand sir. My understanding is that there are two approaches. One is, you follow the person in front of you. The other is, there is a leader for each swarm, and
Okay.
that leader controls how the swarm should operate. So
Oh,
that's
okay.
my understanding of, how the swarm works. In very little what I have read on the swarm implementation. So, yeah.
Yeah, I think just to add upon, I think these algorithms, so-called bio-inspired algorithms, are sort of scalable because they rely on local interactions rather than sort of
Right.
global control. You're right.
Right.
Yeah, thank you.
Yes, sir. I'll definitely work on it in the future, sir.
Wonderful. It's an interesting area you've taken up, Akash. I think you should go all the way and get into research and take it further. Okay, and not
Yeah.
just a college project. Or don't stop here. Take it
Yeah.
further to in-depth research and yeah.
Of course.
With all your blessings, definitely, sir.
Akash, I hope you're also aware of IIT Madras. What is it called? Mm, I forgot the name of it, wherein they support people, Pravartak,
Research.
IIT Madras Pravartak. I hope you're aware of it, Akash. I think you should approach them for your kind information. In fact, last week I apparently met the CEO of IIT Madras Pravartak, Shankar Raman. He's the CEO. And I came to know that they are encouraging students wherein when they find a small project which is sort of successful, and when they are able to prove in a smaller dimension, they are willing to spend 1 crore per student per project. They can go up to 1 crore. So I think you should check on that possibility as well. Pravartak is the name of the subsidiary under IIT Madras. Please check on that possibility, and I'm sure that they'll be more than happy to take this forward, because most of the students nowadays, they look at only job. I think current students should start creating jobs than going for jobs. That can happen only when we focus more on research. Thank you. Great job, Akash.
Thank you, sir. Definitely. Thank you for your valuable guidance as well, sir.
Akash, if I may ask, and I'm hoping this could inspire other students. What led you to take up this topic?
So I was heavily fascinated in how UAVs work because I am heavily fascinated on the flying objects or moving objects. So I was keen to learn that AUV and other stuffs. So I pursued the learning on that, sir.
Excellent, excellent. Wonderful. Good done, buddy.
Yeah. I think you should, pursue your passion and take it forward. I'm sure that, it will have its due recognition, and I'm sure that, anybody for that matter, any sponsor for that matter could be able to come forward and take it up. All the best. Akash.
Definitely, sir. Thank you. And I'd like to mention my department of BCA from SRKS. They helped me a lot while learning in this platform. So I'd like to help SRKS BCA department. So thank you for all of your guidance.
Wonderful.
I think if we do not have any further questions, let us proceed further. We are already 20 minutes past 8.
But time worth spent, sir. Really very nice. And thanks a lot, Mr. Saravana Kumar and all others for this wonderful session. Right? We have to keep this going on, right? Very fourth Saturday, student-led webinar that should go on.
Yes.
As the conclusion of today's webinar, I would now call upon Dr. Raj, CSI member, to deliver a word of thanks.
நன்றி மறப்பது நன்றன்று, நன்றல்லது அன்றே மறப்பது நன்று. Now I am going to deliver the vote of thanks for this student-led workshop. Actually, I would like to record my sincere thanks to Computer Society of India, Region 7, and all the chapters, presidents, past presidents, many senior professors. You all came at that too on a weekend for spending your most valuable time to encourage the students. And it is really a great opportunity for the students of fraternity as well as teaching fraternity to look into all these dimensions. And the very big professors are here, people from industry, and many students. Everyone we have amalgamated here for a noble cause, that is for empowering the students. And today's session actually definitely would have been a eye-opener for many of the students in this forum who have joined in this student-led webinar. Certainly, particularly I want to tell about Mr. Akash. He presented and he obtained many awards and recognitions, not only for doing the research, he did it out of his own interest and passion, as he rightly pointed out. So I once again, I want to thank the Computer Society of India for creating such a big platform for the students, and thank everyone, every single noble soul who joined here and shared their opinion, and even our person from technical, that is from industry, he gave a very big dimension, that is he talked about IIT Pravartak. So with the help of you, sir, definitely we will keep in touch with you and make our students to involve in this research dimension. And thanks to one and all present here very much. Jai Hind.
Just to add up on, I just want to request all of you to do join. This is actually going to be a monthly, student-led webinar which has been started up. So we want to keep the ball rolling, and stay tuned.